Okay, in the last few videos, we have talked about vector spaces and subspaces, and then we talked about linear independence and linear dependence, and we talked about spanning sets for a vector space, and essentially we've created this structure, this thing called a vector space, and now we have these things like linear dependence and independence and the span of a set that kind of put more structure on that vector space and allow us to compare and look at different vector spaces. Today we want to kind of do some formal definitions that tie that together and allow us to really get a focus on what's going on. So we want to look at what's called a basis. And I will point out that word basis is singular. The plural of basis is bases with an E. So that's a basis. If I have several of them, I have bases, which obviously sound the exact same. So just be aware of that as I'm talking. Normally, I'll be using it in the singular case, but whatever. Okay, so the actual definition we want. A set of vectors S equal to V1 out to Vn in the vector space V is a basis for V if 1, the span of S is equal to V, and 2, S is linearly independent. And we're going to work through a lot of examples to kind of get an idea of what a basis is. We've looked at a lot of vector spaces. Now we can kind of go back to all of those vector spaces and try to find a basis for them. But again, the idea of this basis, one idea is maybe to put a structure and an order on the different vector spaces that we have. So I need to create a set of vectors within a vector space where the span of that set is equal to V, which means it has to be big enough, whatever set I come up with has to be big enough that linear combinations of those vectors can generate the entire set, the entire vector space. But it also has to be linearly independent, which means the vectors cannot be multiples of one another. So it also has to be small enough that I don't have multiple copies floating around. So again, I'm essentially finding the smallest possible thing that is also big enough to span the entire space, which, again, essentially, if I look at different vector spaces, will allow me to say, okay, here's a basis for this one. This set generates the entire space, but it's also small enough that everything is linearly independent in that set. And it gives me a nice way to structure and compare different vector spaces. Let's see. One thing your book does kind of point out within the margins, so to speak, a basis does not have to be finite. We'll see an example maybe later on, or at least kind of mention it, where a basis is not finite. They do not have to be finite in general, but for the purposes of what we're doing, our bases should be finite. It's actually pretty easy to see how to expand from a finite to an infinite one. We'll see that, like I said, with an example we'll do in a few minutes. But just be aware, in general, they don't have to be finite, but the ones we look at generally will be. Okay. And, well, no, we'll save more definitions for later. Right now, maybe a couple of examples. Suppose S is equal to 1, 0, and 0, 1. Is that a basis for R2? In order to show it's a basis, we have to show that the span of S is equal to R2 and S is linearly independent. And it's pretty clear to see. We already showed the span of this and a lot of vectors like this in R2 and R3 and so on, that the span of this will easily be all of R2. So the span of S equals R2. Sure, we already showed that one earlier. As far as linearly independent, different ways you could go here. And again, I stress this because we've seen a lot of definitions, and from, I guess, a student problem solving perspective, there's the question of, okay, how do I go about doing this? Well, one way we said things are linearly independent is if the vectors in your set are not multiples of one another. In this case, that's clearly true. I can never get a multiple of this that will give me that. You can have a collection of vectors where maybe that's harder to see, so that wouldn't be the best way to go. Here, that's clearly obvious. I can never get a multiple of this one that will ever give me that one, and vice versa. So they're linearly independent. Another way to show it, maybe the more standard algebraic way of showing it, is using the homogeneous system. So we could do C1, if I call this V1 and V2, my vectors in my set S. C1 V1 plus C2 V2 has to equal 0, and I have to show that it has a unique solution, and that solution is the 0, 0 solution. But clearly, C1 V1, which is 1, 0, plus C2 V2, which is 0, 1, equals the 0 vector, which is 0, 0. Clearly, the only solution is C1 equals C2 equals 0, which again shows that it's linearly independent. So you can always fall back on creating a homogeneous system with the vectors in your set, setting it equal to the 0 vector, and then solving it out and showing that all the C sub i's have to be 0. But again, there are other things that we can use. In this case, the idea that they're not multiples of one another, which is obvious to see. So that's another way to say it's linearly independent. So be aware, there's kind of the standard approach, but we have a lot of definitions and theorems and all that. A lot of this is interrelated, so there are different tricks you can use. Okay, good. But that means 1, 0 and 0, 1 form a basis in R2, or for R2, I guess, grammatically. Which means any vector in R2 can be generated by those two. That's pretty obvious. And those are not multiples of one another. So that kind of gives us a little bit of structure in our R2. But it does raise maybe a little bit of a question. What if I had the set S equal to 1, 1 and 1, 4? Does that form a basis for R2? Can a vector space have more than one basis? Well, really quickly, we'll go backwards here. Linearly independent? Sure. Again, in this case, I'm not even going to bother setting up the system. Those are clearly linearly independent because I can't write one as a multiple of the other, which means they're linearly independent. Does the span of S equal R2? Well, there's different ways to go here. We could set up a system. C1, we could, let's see, pick X equal to X1, X2 as an arbitrary element in R2. Then we could set up a system. Let's see, coefficient would be 1, this v1, v2, and set up my system. C1, v1 plus C2, v2 has to equal x. But then I could create my coefficient matrix. Coefficient matrix, let's see, would be 1, 1, 1, 4 has to equal x1, x2. And then I could solve that out. Again, there's lots of different ways to go here. I'm trying to list out several of them so you see all of them. But in this case, we could solve this out. But even without doing all the elimination or whatever, two equations, two unknowns, we know they're linearly independent. This is going to have one unique solution. Which means I'll have values that I can plug in here, which means I'll definitely be able to write x1, x2 in terms of v1 and v2. So that will definitely span R2. Which means that this S is also a basis for R2. And could I come up with other sets of vectors that will give me a basis for R2? Well, yeah. As it turns out, as long as I have vectors that are linearly independent in R2, then I'll get a basis for R2. Which means, and keep this in mind as it is important, your bases, plural bases, are not unique. You can have more than one. Which means, when we have basis like this one right here, this one we call the standard basis for R2. The standard basis for R3 would be the same, but it would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Essentially, ones in each place and zeros everywhere else. Those are the standard ones, and they're the ones we use most often because they're standard and nice and neat and all that. But there are lots of other bases. So don't say, read a problem and say, is this a basis? No, because it's not this one. That's not how it works. You can have a lot of different bases that we'll see. Maybe the question that would naturally come up then, again, from a student perspective, well, this basis in R2 has two vectors in it. This basis in R2 has two vectors in it. Could I have a basis with one vector? No, that's really unlikely. Could I have a basis with three vectors? We'll actually see a theorem at the end of this video where we go over that and kind of determine the rules as far as that goes. Or you can kind of think about it algebraically. If I had three vectors in R2, could they form a basis? Would they span R2? Would they be linearly independent in R2? Something to ponder as we do more of these, and like I said, we'll come back to it. But again, with this standard basis in R2, we get standard bases in Rn. In Rn, S equal to, easiest way to write this is maybe 1, 0, 0, 0, 0, 1, 0, 0, 0, etc. out to 0, 0, 0, 1. That's my standard basis in Rn for any n. Ones in each spot and zeros everywhere else. And whatever n is, that's the number of vectors that will be in your basis. In R2, there's 2 of them. In R7, there's 7 of them. That's pretty clear. We have looked at other vector spaces. So just to run through a few more examples. Let's see, I have a bunch that I wanted to go through. Let's see, here we go. Polynomials P3. So here the polynomials of degree 3 or less. What would form a basis for those right there? Well, there's different ways to go. But maybe it would seem the easiest way to start. Let S equal 1, x, x squared, and x cubed. Is that a basis for polynomials of degree 3 or less? Again, we do the check. 1, we'll go backwards again. Linearly independent. Here, much like with the last ones in R2, it's pretty clear. These are not multiples of another. Keep in mind, when we say multiple, we don't mean multiply together. We mean a constant times each vector. No matter what constant I multiply by each of these, I'll never be able to get the square from the x or from the x cubed or whatever. I'd have to multiply them together, which is not what that means. Which means they're clearly linearly independent. 2, the span of S is equal to P3. But in this case, an arbitrary vector in P3 is a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed. But that's literally exactly what I would get from these vectors. It would just be the combination a1 times a sub 0 times 1 plus a sub 1 times x plus a sub 2 times x squared. So again, just by the actual definition of the polynomial, that gets generated by 1x, x squared, and x cubed. So clearly, those will span R3. So they're linearly independent, they span R3, that's a basis for P3. And again, can you come up with other bases? Yes. For the purposes of this is the standard basis. And by extension, that kind of tells us what our standard basis for P sub n will be. 1x out to x to the n will just be my standard basis. Keep in mind, if you're kind of running all this stuff through your head, when we were talking about Rn, R2, the basis had 2 elements. R3, the basis would have 3 elements. Here, in P3, my basis has 4 elements. So in Pn, my basis would have n plus 1 elements. Which means you have to think clearly about what it is you're actually doing. Don't just say, oh, there's a 3, the basis has 3 things in it. Oh, there's an n, the basis has n elements in it. It varies based off of the type of vectors in your given vector space. Next up, we did vectors in Rn, polynomials, matrices. So we'll say M22, kind of the standard 2x2 matrices. And, okay, that is my vector space. My set S. Suppose it's this, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Suppose that's my set. Is that a basis for M22? Linearly independent? Once again, there is no way to get one of these by a multiple of a different one. Essentially, it's the exact same argument as we did with the vectors. These are just matrices. There's no way you can write one as a combination of the others, which means it's not linearly dependent, which means it's definitely linearly independent. Span. Does S span M22? Well, sure. Again, if I pick an arbitrary vector in M22, x11, x12, x21, x22, that's clearly equal to x11, v1, v2, v3, v4, x11 times v1 plus x12 times v2 plus x13 times v3, x21, my brain automatically counted upwards, and x22 times v4. So clearly, any vector in M22 can be written as a linear combination of those. Which means that that will span M22, and that's a basis. And again, that one should be obvious. It's identical to our bases for Rn. 1's in one slot, 0's everywhere else, accounting for every slot possible. There's no smaller set where essentially I have one with all zeros. I've kind of made it as small as possible. A 1 here, 0's everywhere else, a 1 here, 0's everywhere else. I can't do anything less than that and still guarantee that it's linearly, that it will span the entire set. But it's also, if I make it any bigger, if I put some other vector on here, then I'll be able to write that other vector. If I arbitrarily put this vector in there, 1, 3, 0, 0, well, now clearly I can take a combination of v1 and v2 and get this one. 1 times this plus 3 times that. So this is the smallest set that is both linearly independent, no multiples of each other, but will still span everything. And again, there are different ways to prove this, which is why I'm doing it different ways on all of them, because ultimately this is what you will do. Hey, here's a collection of vectors. Is it a basis? You have to check if it spans and if it's linearly independent. There is the long form argument. In order to span, pick an arbitrary vector, write it all out, do the algebra, show that you can generate that arbitrary element. Linearly independent, write out the equation, and then show that the only solution to the homogeneous equation is the trivial solution where all your coefficients are 0. But there are other tricks. This idea of one is a multiple of another, or if you're given a collection of vectors, again, say this was still here, is that a basis? No, because all 5 of them are not linearly independent. So then, start removing vectors until you get a linearly independent set, and then see if that's a basis. So there's different types of questions and different ways we work with this, so be aware. Okay, now, how long is this audio? We're 25 minutes, okay. So we have a few theorems, and then another really, really important idea. So we'll go through the theorems really quickly. You're going to prove at least one of them for homework, so we won't really go to proofs here. If S is equal to V1 out to Vn is a basis for the vector space V, then every vector in V can be written in only one way as a linear combination of vectors in S. This one, I actually am sure that I assigned you for homework. So we won't prove it. But the idea is, if I have a basis, think about it in terms of R2. My basis was 1, 0, and 0, 1. So I have a basis. Then every vector in V can be written in only one way as a linear combination of vectors in S. If I pick some arbitrary vector, 7, -2, how many linear combinations can I make using those two vectors to get that. Clearly, there's only one. 7 times this and negative 2 times that. That's what this is saying. Since this is a basis and they're linearly independent, they're not multiples of one another, then every vector can only be written in one way as a linear combination. We'll see this later on in this chapter, later this week, but the idea is, well, if I start, say, using these ideas to solve problems, then ultimately I'm going to have matrices and coefficient matrices and sets of equations again. And if somehow I can only write my solution in one way, that means my solution is unique. So the solution to my system will be unique. And then maybe, we had mentioned this way back when we first did systems of equations, maybe there's this relationship to linearly independence, which is coming from this basis, and how many solutions there are to a system of equations by way of the matrices. We mentioned that earlier, and now we're going to kind of start to see how those things work together. But I will leave the proof and all that to you. But next up, if S is equal to V1 to Vn, is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent. And there's a follow-up to this, which we're going to do, and we'll kind of look at these together. Theorem. If vector space V has a basis with n vectors, then every basis has n vectors. Okay, now when I grab a swig of Gatorade, ponder those two. Okay. If S is V1 to Vn is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent. And again, the idea, essentially what we were just saying, in R2, if I have 1, 0, and 0, 1, if I add a third element to that, let's see, that's a basis. Every set containing more than n vectors is linearly independent. If I throw another element in here, 2, 4, is that independent? No, because I can write this vector as a combination of those two. And what that really means is, once we have an idea of what bases are or how big a basis has to be, then if I'm looking at a collection of vectors, if I want to know if that collection of vectors is a basis, I can do the test, or I could say, well, no, that can't be a basis, because here's a basis that I know, one of the standard ones, and it has 7 elements. The set S I was given has 8. So one of those vectors has to be a combination of the others. And again, the principle, the idea being, suppose S is equal to 1, 6, 2, 5, and -3, -4. Is that a basis for R2? You could run through the sets, you could run through the tests for independence and for spanning, but I know a basis for R2, and it has 2 elements, that set has 3 elements in R2, which means it has to be linearly dependent, which means it's not linearly independent, which means it's not a basis. So again, I'm not going to worry about the proof, it's pretty straightforward algebraically, but it gives us another way to determine if something is a basis or not. You can use the definition, or if we keep in mind the standard bases that we know, we can look at the number of elements in those bases. Okay, if a vector space V has a basis with n vectors, then every basis has n vectors, which is obvious. Again, if I have a basis here with n vectors, say S, if this is another basis, say S sub 1, and it has more vectors than that, then according to this, it would have to be linearly independent, which means it wouldn't be a basis. On the flip side, if this basis had fewer vectors than that, well, then this couldn't be a basis because of, well, this. So once I know the size, the number of elements in a basis of a vector space, then I know the size of every basis in that vector space. They can't be more, they can't be less, they're always the same. That's again why we have these standard ones, because they tell us immediately, oh, R7, basis has 7 vectors. That does not mean any collection of 7 vectors is a basis, but if the collection has fewer than 7 or greater than 7 elements, then it can't be a basis. Then all I really have to check is if those 7 span the whole thing and are linearly independent. Okay, but these at least give me a starting point when looking at my collection of vectors. Which leads us to the last thing we want to go over today. Since the size of the set that forms our basis seems important, we have what's called the dimension of a vector space. If vector space V has a basis consisting of n vectors, then n is equal to the dimension of V. When V has only the 0 vector, then the dimension of V equals 0. And again, now the idea is the basis helps me put a structure on my vector space and give me an idea of what the vectors look like in that vector space. And clearly, even if I can have different bases, they all have to be the same size, which means that size seems to be important. So now we'll classify vector spaces by way of the size of their basis. We call that the dimension. So again, we've already kind of touched on it. For Rn, the dimension of Rn is equal to n, because any basis in Rn is the standard basis with 1s and 0s. For P sub n, polynomials of degree n or less, the dimension of Pn is n plus 1, because we have that constant vector that we have to throw in there, the 1 at the beginning, so to speak. Matrices. For m, that looks terrible, but m to the mn, matrices of order mn, the dimension of mn is equal to, well, think about it. I'll use the same principle we did here and with the 2 by 2. I'll put a 1 in each entry and a 0 everywhere else. So the dimension will be m times n. That's how many matrices I'll need for a 1 in each entry and 0 everywhere else. So then, how do I use this? Once I know what a vector space is, and I know what a basis is and how to find a basis, now I know that there's this relationship between a basis and the dimension of the vector space, and the fact that whatever the dimension is, which is the size of the basis, that has to be consistent with all of the other possible bases. Then I just get a few little tests, which I'm checking the video time, 35 minutes, okay. Tests that we can use to help us determine if things are bases or not. So let V be a vector space of dimension n. 1. If S equals V1 out to Vn is linearly independent, then S is a basis. And 2, if S equals V1 out to Vn spans V, then S is a basis. So we have our basic definition of a basis of a vector space. The set has to be linearly independent, and it has to span the whole vector space. Here, these say, if you have a vector space with dimension n, then if your set S is linearly independent, it's a basis, or if it spans, then it's a basis. And keep in mind here, what this is really saying is, again, for a given space, we'll use R2 again, 1, 6, -2, 3. Can I write one of those as a combination of the other? No. So they're linearly independent. Does it form a basis? The definition says I would have to show that it spans R2. So I could write out my system and go that way. But what this says is, in R2, I know the dimension of R2. It's 2. We know my standard basis. Since the dimension of the vector space is 2, and these two are linearly independent, they form a basis. By the same token, if I say in R2 had 2 vectors that would span the whole space, since I know the dimension is 2, they form a basis. And again, all this really does is gives us tricks to maybe save time. Could I show that these span R2? Well, yeah, I could set up a coefficient matrix, do the algebra. We could actually use some of my old theorems that since I have 2 equations, 2 unknowns, ultimately I'll get one solution. The solution is unique, however you want to say it. There's lots of different ways we've done this. This just kind of formalizes all of that. So, for an arbitrary vector space, if you do not know a standard basis for it, you can always do the check. Linearly independent, and does my set span the vector space? Both of those work, it's a basis. Alternatively, if you know the standard basis for your vector space, then you know the dimension of the vector space, then you really just have to show one, linearly independence or spanning. And generally speaking, one is easier to do than another. I mean, for a lot of them, this idea of one as a multiple of another, it's pretty easy to see. So it allows us to save time on our work by essentially combining all the different ideas that we have. We're going to expand on this because there's always more to do throughout the week, but I think this one is long enough.